Yeah, it is really an historic moment. I mean, when Parthoda invited me for this one, it was a really, it's a wonderful feeling, I mean, I would say. And yeah, so we are celebrating, I think, one of the greatest moment. And of course, I mean, all of us has a different connection with ISI and Professor Rao in a different way. And well, I was one of his students towards the end. In fact, Provala was asking me, were you the last student? Well, I said that no, I am not the last student, but towards his end, when he was at Pittsburgh, and then actually I finally got my degree from Penn State because he moved to Penn State, and I got the degree in Penn State. And in fact, again, Parthoda was telling me to choose a topic, and I thought that this should be the best thing for me to say. First of all, this is the one thing I know a little bit about it. And second reason is that because we know about Professor Rao's contribution in all the other fields. I mean, nobody has to tell how much he has made the contribution in inference, design of experiments, and economics, econometrics, and all these things. But I think not too many statisticians are familiar with about the kind of contributions he has made in statistical signal processing. And it's a very interesting one. I mean, I think he has worked in this, he himself has worked in this particular area not a very long time. I mean, I think he has started in the early 90s, and basically he has worked maybe around 4 or 5 years. Of course, I will show you the publications he has done. He has some paper after than that, but those are, I would say, kind of a spillover. But I think the implications, what he has made during those time, I think that is a very far-reaching consequences. And I think one word I would say, the main implication about his contribution in this particular area is the way of thinking. I think that he has completely changed, that the way of thinking about dealing this problem. And in fact, I have to tell two things. First thing, I'll show you this one, that the fundamental model, what he has worked on. I'll come back to this one. But the second one, I was in sabbatical at Penn State in 2000, and as I was giving a talk, and he said that, oh, you can still find, and by that time he was not working that much on the signal processing. So he said, oh, he's still finding some interesting problem in signal processing. And well, it was 2000, which is 20 years back, and still I can find several interesting problem because the way he has changed the thinking process. That's the way it is. Okay. So anyway, let me start. First, I think I'll start in a slightly different way. I mean, first I will show that the publications what he has in the statistical signal processing during the time he has worked on this one, and then I will come back to my presentations and the fundamental models and what kind of things which has been done and which can be done also. Okay, so yeah, so as I said that, I mean, he has worked in the early 90s, and actually his first publication in the signal processing on this particular area. Actually, this again, I mean, I think I should mention these things. I mean, these are the direct problems associated with the statistical signal processing. Although he has a couple of papers with Professor Khatri and all these things, which are mainly the statistical problem, and they can be applied to the signal processing, but I'm not including those things. These are the purely signal processing problem what he has dealt with, and so these are the publications mainly related to that. And by the way, I think I should tell this one, this IEEE transaction signal processing, the topmost journal, which is like the Journal of American Statistical Association. So that is the first one, that is the first paper what he has, and then he has this paper, and yeah, so he has many papers on this IEEE signal processing during that time. This is the one which is like this, the similar version from the Europe, from England actually, IEEE Proceedings F, which is also on the signal processing one. And then he has actually a book volume. They had published the Handbook of Statistics with Professor N.K. Bose. He is a famous signal processor at Penn State. So they had done this book on this signal processing, almost like 1,000 pages.
These signals are not based on IID observations. These are dependent observations.
All the things.
Yes, all of them.
No, not all of them. I mean, all are different assumptions are there. It's not only the IID. IID is there, stationary is, all sorts of things are there. It is there. Okay. I'll come back to the model. We'll see this one then. Okay. And yeah, so these are the different one. And in fact, he has a paper in this, the Proceedings of National Academy of Sciences with Wu, who has given the presentation yesterday. That is the one. And yeah, so he has this paper. So these are basically the signal processing paper what professor has directly on this application. So now let's come back to the fundamental model what he has worked with. And yeah, so this is it's a very simple way to put the things. I mean, it's the model what he has dealt with, which is this model. Okay, so this YT, which is a sequence of complex valued observations satisfying this particular assumptions. Okay, so YT is equal to summation AK e to the power I omega KT plus epsilon t, and here AKs are complex valued amplitudes. That's what they call in the signal processing literature. And omega k's are the frequencies, and the epsilon t's are complex valued noises. Well, it can be, as he's saying, it can be IID, it can be stationary. So depending on the error assumptions, the estimation procedures, the properties, and all these things changes.
What exactly is meant by complex value?
Well, so these are the, so you can see this one, that my AKs are complex number. I mean, if you put it this way, yeah, so these are all complex number. Your I is square root of -1, so omega k's are between 0 to 2 pi. So it's basically your YT is a complex number. That's it. So basically what you have these YTs. So these epsilon t's are complex valued noises. So again, it can be a complex multivariate normal or dependent something. So these are, everything is complex. Everything is complex. So basically your YT, which is a complex valued observations, that's what we have. So this is the model. And again, I mean, let me tell you this one. Say when I just finished my comprehensive and wanted to work with him, so it's very unlike a Professor Rao, because he usually does not give the problem. I mean, everybody knows this one, that he basically gives an area. He said that one, you start reading and we discuss, and then the problem will evolve. But for me, I think, well, I think I say I would lucky in that respect, because he, I think, was just observing those things. That was way back in '86. So he got two theses, one from the mathematics one, another from the electrical engineering one, and so they were dealing this problem. And in fact, when I showed my intention to work with him, he gave me this model, and he told this one that, look, I think these people are trying to solve this problem. I mean, as I said, one is a mathematician, another is an electrical engineer, the two theses, and he said that, well, if you can solve this problem, I'll give you a PhD. Okay, that was his thing. And so now, I mean, the thing is that it is, then when I started reading, of course, I mean, that time I was completely new. It looks like a one problem, but then of course we'll go back, and actually it's a class of problems. Actually, it is not only one problem; it's a class of problems. And in fact, it's very interestingly, in '88 we saw a paper again in the Signal Processing Journal, which lists the number of references on this particular model which has crossed more than 300. Just the number of references. I mean, it just said the number of references on this classical model which crossed 300. So it's a very, very classical model, because it has lots of implications. It has lots of generalizations. So that's what he has.
I'm still trying to grapple with this. I know nothing about this area. So YT is a signal at time t.
Exactly. YT, yes.
Is it a complex number?
I'll come back to this one. Yes, I'll give this one. Yes, exactly. So that is definitely, so that was the same question I had also in my mind when I started working on it. Yes, I'll come back to that. Yes, definitely. So the problem is very simple. I mean, if you look at it, the problem statement is very simple, because if you go back to this model, so this is basically the summation of K, summation of P summation of these, what they call these exponentials, complex exponential or complex sinusoid. And so basically, problem is estimate P, estimate A1, A2, AP, they are complex number, and estimate omega 1, omega 2, omega. It's a very simple one. So basically, that is the problem. I mean, you have this YT, that is observations what you have, and so under different error assumptions. As I said, I mean, epsilon t is, you make different error assumptions. So now let's see, as he is asking, the natural question is, why a complex valued model? I mean, that's a natural question, because all our signals are real valued signal. So what do you mean by the complex valued one? Okay, so let me go back a little bit and see this one, that how this model arrived. And so actually all came from the periodicity of the signals. Okay, and that's what basically the genesis of this one. And so let me just try to explain. I mean, we observe the periodic phenomena every day in your lives. I mean, that is true. I mean, you're looking at the number of tourists visiting the famous Taj Mahal, or you're looking at the daily temperature, or you are looking at the ECG data. I'll show you some of the pictures, and you will see this one, that there is the periodic pattern. Okay, that's a very common one. Sometimes the data may not be exactly periodic, but it is nearly periodic. Particularly, it is because of the noises and things like that. And so our main aim, I am trying to analyze this periodic or this nearly periodic data. So that is at the end of the day. Okay. So the natural question is, I mean, what is a periodic data? I mean, how do you define a periodic data, and why do you want to analyze a periodic data? Okay. I mean, these are the simple questions which naturally comes to our mind. I mean, what is the necessary for that? Well, I mean, I'm not going to give a formal definition of the periodic data, but I think it should be clear. But informally speaking, periodic data, if you look at it, it shows the periodic pattern. Okay, it's a repeated pattern what you see after a certain time. That is in one dimension. But it is not necessarily that it has to be in one dimension. It can be in a higher dimension also. We'll show some of the pictures, and you will see this one, that it's a symmetric pattern in a higher dimension. So which basically means those are the periodic data. Okay, that's what it is. Okay, and why do you want to do this one? Or why do you want to analyze that? Well, I mean, definitely one of the very important thing is that we have to predict. We have to predict in the future, and that comes out because of the periodic one. It becomes quite meaningful, and that's what we'll see. That for the prediction purposes, it is definitely it's a very useful one. We'll see this one, that this is another very important point, or any very important area. Particularly all these signal processors they are working on, they call this compressions. Okay, the compression of the data, and that is also being extremely useful if you have a proper model of this kind of data, and it can be used enormously for the compression of the data. Say, for example, one of the very simple examples which comes to my mind always, that particularly suppose you have a huge amount of data, say for example ECG data. These are all periodic in nature, and we'll see this one, that rather than keeping the whole data, you can compress it using the model, and which we can save it in a very easy manner. Okay, so that is one thing. And another one is the comparison purposes, and so this comes under in the statistical framework, what we call this one as the testing. And we'll see this one, that well, suppose you have ECG data for a normal person and from an abnormal person, and you want to test. Okay, you want to test whether this person is abnormal or not. Okay, so that can be used as a comparison purposes. So these things are actually very practical meaning, practical importance on these things. Okay. Yeah, let's look at a couple of pictures. I mean, this is one of the famous data set where it says the airlines passenger data across the time. You can see this one, that this is basically the month, and you can see this one, that there is a pattern, there is a periodic pattern which keeps on happening, and these are basically the summer time. That's what it is. So the number of passengers it increases during the summer time. That is there. This is another, the brightness of the variable star, which basically measures the distance of the star from Earth, and again it varies, and because of this one it comes closer and then it goes far away, and that's the way there is a periodic pattern in this one. This is a vowel sound. Actually, this is the sound which has been taken at IIT Kanpur itself in the signal processing laboratory, that when you utter the particular sound, and you can see this one, that there is clearly a periodic pattern in that one. Yeah, this is the ECG data of a normal person, human being. Again, you can see that there is clearly the periodic pattern. Okay, so these are all in the one dimension, and actually we can have the same thing in the higher dimension also. If you look at the 2 dimensions or the 3 dimension also, you can see that this is basically a texture data, which is a periodic data in the 2 dimensions. These are called the grayscale images, which is the black and white, and so this is, you can see that there is a symmetric pattern in the 2 dimensions. Okay, so this is basically a 2-dimensional periodic data. Similarly, what we have, it is a 3-dimensional periodic data what we have, because the color is there. So there is another dimension which is on the 3rd dimensions. So there is clearly a periodic pattern, that means a systematic pattern on the 3rd dimension also. Okay, this is also another periodic data. So these are the things, which is very, very common, that you will see this one, that this periodic behavior. So what do you do? I mean, you have let's look at the 1 dimension, and then of course I'm not going to go deeper into the 2 dimensions, but the similar thing can be done even in the higher dimensions also. But let's look at in the 1 dimension case. Okay, so the basic formulations. It's a very simple one. It's basically, I think it's a class 10, 12 things what we have seen when we have first studied all these trigonometry. So this is a very basic one. I mean, we are looking at the periodic pattern. Okay, so there is a period 1. So if you have any periodic function yt, you have simply this a cosine omega t plus b sine omega t. Okay, that's a basic the periodic function you can think of, which repeats. Okay, and basically the yt is the shortest time taking the period is the shortest time taking of yt to repeat itself, and it is 2 pi by omega. That's the way it is. And actually we have this standard, the Fourier transformation, Fourier expansion of any periodic function. We have this infinite expansions, which is well known, that yt any periodic functions has this infinite expansions. And
P.
Yeah, so this is that will come. Yeah, so that's what is going to happen. That's any periodic functions, it has these expansions. Okay, any periodic functions, and you can extract these AKs and BKs from these YTs, and which is simply nothing like this one. Okay, so you can easily extract these AKs and BKs from the YTs by simple this one. This is the standard Fourier expansion of any periodic functions. So that's what it came. So what you do? Well, I mean, in practice, we do not have the all the time we do not have the real data. I mean, we do not have the exact periodic function, so you observe with error. Okay, that's a very standard one, and that's the reason this one that we have this error xt, which is a noise component, and that's what my yt is, which is summation ak. Still same thing with k is equal to 1 to infinity plus xt. That's how it is. But the problem is that we have an infinite number of parameters. So from the yt, which you observe as a signal, so for example, the ECG signal or whatever it is, it may not be possible to estimate this infinite number of parameters. So that's the reason that we truncate. We truncate this one, and we make the model slightly different, and that's what it is. So you can see this one, that my omegas are fixed here, and that's the difference what we make, that we make this one, that yt, which is, we chop it at the point kp, and I have this ak cosine omega kt. That's the reason that these things have changed. Okay, so that's what it is. And the complex model, what it is, which is simply nothing but the complex version of this one, or you take the Hilbert transform of this one, and you got that model. So either you work with this one, doesn't really matter, or you work with the complex model. Both are equivalent actually. So from this real valued signal, you can easily get that complex one, or the vice versa also. Okay, so that's the reason this one, the complex model comes into picture. And so the problem is very clear-cut problem. I need to estimate my p, I need to estimate my AKs, and I need to estimate omega. That's what it is. Okay, so yeah, so basically I need to extract the deterministic component mu t, which is like this, in the presence of the error component xt, based on the available data yt. So that's what my problem formulation is. Okay, so let's look at a different estimation procedure which has been tried for quite some time, and what was the problem associated with it. Okay, I think that is important. And as I said, this problem is this engineers or these electrical engineers are working with for maybe last more than 100 years. And the standard technique, what they say, that the periodogram estimator. And the idea is very simple, and idea is nothing but,
Can I ask a question?
yes.
If you increase P,
Yes.
the model fitting will get better and
Exactly,
better.
exactly. So there is a threshold. There is a threshold, this one that, well, see, the standard model selection problem, I mean, if you increase P, of course your model fitting getting better, but your error variance is getting increased, okay? So there is a compromise. I mean, that's a standard model selection problem. I mean, so what should be the optimum P? That's what it is, okay? So yes, I mean, that's the reason that I said that estimation of P is an important problem. I mean, that is there, okay? So yeah, so let's look at that. I mean, the way it has been handled by this one, what are the nice part and what are the difficulties, okay? So the problem, what they have done it, they call the periodogram function. Actually, it has a slightly different representations in terms of the complex one, but I think we can put it in a very, very simple manner, which is simply nothing but, so you have this yt, what you observe, that's the data what you have. You simply look at this particular function I theta as a function of theta. So your theta varies between 0 to pi, 0 to 2 pi, and you are looking at this particular function, which is approximately equal to this quantity. And I plot this quantity as a particular function, and you'll see how does it behave. Okay, so this is basically, let's look at a simple sinusoidal model with two components. So I have my 3.0 cosine 0.2 pi 2.02, 0.2 pi t plus sine 0.2 pi t, the first component. And the second component also had the same bk, but I have the same different omegas. Okay, so I have two different omegas, so there are two components. That's the model I have, and I have my xt's, which are IID normal 0, 0.5. Okay, that's what I have, and I simply plot this particular function I theta as a function of theta, and the plot is like this, which is a very, very nice one. I mean, you can see this one that well. Actually, this is nothing but your omega 1, which is 0.02 pi, which is nothing but this component, and this is my second component, which is nothing but my 0.5 pi. Okay, so that's what I have, and I have and there are two components which are very, very clear. Okay, so this has been used for quite some time. This one, and actually it works very well. I mean, you can see this one that, okay, because if you have this one. But if you look at a slightly different one, slightly different model, same sinusoidal model, I'm looking at it. I'm looking at it 3, same thing, cosine 0.0 pi t, sine 0.02 pi t, plus 0.25. Instead of 3, I have 0.25 and the same one. And now I'm plotting the same function, I theta function, for this particular one. So again, you can see that it's a sum of two sinusoidal. Only thing what I changed, my AKs and BKs have changed slightly, okay? And I'm looking at everything else is same. And now we can, and the error variance has increased, I'm making it to 2.0. And now if you plot it, you can see only 1. So that means one component has gone. So looking at the plot, definitely it is not clear. So the problem is, you can see this one that although at the beginning it looks quite nice, that model works, the method works quite well, but it is not going to work for all kinds of model. I mean, even if you have a simple model like this, that's what it is, okay? And so that's the reason this one that, well, our statistical problem, which is the first one, and I think that is the first one they have tried, and of course, the least square estimators, okay? We are looking at the, yes? Yes, I did of Mathematics, and in 1981, they had given a couple of sufficient conditions that if a model satisfies those sufficient conditions, then the least square estimators become consistent and it gives an asymptotic normality results. But unfortunately, what it happens that in this particular case, they do not satisfy the sufficient conditions. So what does that mean? That means you won't be able to apply these results. So either the least square estimators may not be consistent, it can happen, or it may be consistent, but it needs a different proof, because that proof is not going to work, because the results what they have, they are the sufficient conditions, so we need a different proof, and that's what it is. And in fact, it has been proved that one least square estimators are consistent, but the proofs are completely different than the way this has been proved. But one thing what is very, very, I would say it's a very, very, not a disturbing one, but it's a very, very significantly different than a linear regression one, that in case of these AKs and BKs, they have a nice convergence rate as n to the power minus half. But when you look at this omega k's, I don't know, this one has gone, actually it is n to the power minus 3/2. So the convergence rates are different than the usual nonlinear regression model. Okay, so that is, I think, one of the major significantly different issue on this particular model. Yes, please.
When you wrote xt as the error term,
yes.
so then you have to put some covariance structure.
Well, actually, see, I did not see this particular paper. This particular paper, they have done XTs at the IIDs one, okay. But the results what are there, it can be shown this one that not only for the IID, even for the stationary errors also, the results are true actually. Yeah. So the least square estimators are consistent and asymptotically normal, even for the stationary error also. Okay. That is the linear stationary errors also. Those are there. Yes. I mean, so again, it satisfies some of your question also that, well, it is not only true for the IID one, but it is true for the dependent error. Actually, it has gone even further than that. I mean, it can be shown this one that even if it is true for the heavy tail error also, and things like that. Yeah. So those are there. So yeah. So about the numerical one, what can be done that, well, let's look at this one. Let's solve in this problem sequentially. Okay, and that's what it has been done. That, well, we solve it one at a time. And it works in this particular case because the components are orthogonal in nature, because it's a sine cosine component, so they are orthogonal in nature. So you can do it sequentially, and that's what it has been done. That you do one component at a time. Okay, you do one component at a time. So your YT, you try to minimize this quantity, you estimate this one, and then you take out the effect of this one, and you go to the second one, and you repeat p times. Okay. The nice part about this one that, well, you do not lose any efficiency. The efficiency of the sequential estimator is exactly same as the least square estimators, but you gain enormously in the estimation, your accuracy of the. You gain enormously about the timing of that, of the estimation efficiency of the, not efficiency, I would say the timing of the computational time. Okay? So, for example, if you.
It converts to the global.
It converts to the global one, exactly. So, and in fact, it happens just because it has this orthogonal component. Just because it has the orthogonal component, and that's what it is. And
also depend on the initial choice of P.
Choice of?
P.
No, actually, P will be estimated later on. See, that's what I'm saying. We are doing it one at a time. You do it one at a time. So for P is equal to 1, P is equal to 2P, and then at the end of the day, you estimate P also using the model selection criteria. Okay. That's what it is. That's what you do. And let's look at the kind of computational, the computational gain you get. Say, for example, suppose I'm looking at P is equal to 25, actually, which is very much there for your all those ECG signals and all these things. And then actually you need to solve a 25-dimensional optimization problem, which is a nightmare actually. It is not a very easy one to solve a 25-dimensional optimization problem, because you need, that means 25 initial guesses, which is definitely, it's a non-trivial task, okay? But now, what we need now, we just need to solve 25 one-dimensional problem. And getting the initial guesses for those 25 one-dimensional problem is extremely easy. I mean, the simplest way that you can simply plot it and you can get this one. So that is one of the easiest way what you can get this one. So instead of solving a 25-dimensional problem, you just solve 25 one-dimensional problem, and it does not have any problem about the initial guesses or the convergence, and not only that, it produces the same accuracy as the least square estimators. Okay, and in fact, they have the same asymptotic distributions that has been shown. And this is another very interesting one, very counterintuitive, and but it has worked. And it is this one that if you look at the usual, the Newton-Raphson algorithm, which is a very, very standard form, which is nothing but you go from the jth step to the j plus 1th step, which is omega j minus q prime omega divided by q double prime omega. Okay, this q prime is the least square functions. Okay, so you move from the one to the other. That's the way it is. But as I said at the beginning itself, that the usual, the Newton-Raphson algorithm, it does not work, it may not converge and things like that. But interestingly, what we call this one as a step factor modification, if you can make this step factor modification 1/4, of course this 1/4 does not come from the heaven. I mean, there is a purely theoretical analysis for this one. That's the reason this 1/4 came into picture. And if you use this 1/4, then actually it is not only converges, but it produces a lower variances than the asymptotic variance of the least square estimators. And well, the reason is that actually you sacrifices in the biases. Okay, it does not come free. You sacrifices some of the biases, so that means it has a more bias than the least square estimators, but it has a lower mean square error. Not the rate of convergence, but the factor what is there for the least square estimators. This one has a factor of 1/6. Okay, so this is very, very counterintuitive, but this is true. Okay, so these are basically the main theoretical results. The least square estimators are consistent under mild assumptions on the errors, as I mentioned. Least square estimators have the convergence rate, which is n to the power minus 3/2 for the frequencies. Sequential estimators have the same rate of convergence as the least square estimator. Asymptotic variance of the super efficient estimator, that's the reason we call this one super efficient, which is the smaller than the least square estimators. And the periodicum estimators, which I had mentioned at the beginning itself, they are consistent, but it has the convergence rate n to the power minus half. That's what it is. This is a future work, as I said, that implications. I'll just go through quickly, and because my time is up. So this is another chart model which has been becoming very popular for the last around a decade. And again, it's a class of model, class of problem, and which is what we call this one. So instead of alpha t, there is another term which is called this t squared term. And so this is also, it's a very, very popular model in statistical signal processing. And so this is the general chart model what we have. And these are the different applications areas. Is a huge number of amount of applications. It has been used in the audio signals, then music to the animal vocalization of the speech. Actually, it has been used in identifications of the species and things like that because of the hearing the voices, the radar and the sonar signals, and as well as the modeling the EEG signals. These particular models have been used. And so these are the least square estimators. As I said, the least square estimators again are consistent under finiteness of this one, standard one. And the main difference is that if you look at these betas, the least square estimator again has a different rate of convergence, which is n to the power minus 5/2. Okay, here the problem is much more severe, and again the main problem occurs about the how to estimate. And in this particular case, actually you have a nice number theoretic results, which actually helps us in this particular case using this number theoretic results, which are not a very easy to prove, by the way, but it's already exist, so that's a good part. So what can be shown that the sequential estimators, which can be used in this particular case also, they give a consistent estimators. Okay, so that is about the nice part about this one. And there is a number theoretic conjecture actually, which is not yet proved. I mean, and using this number theoretic conjecture, what can be shown that, well, the sequential estimators and the least square estimators, they're equivalent. Okay, so it doesn't really matter whether you use the least square estimators, the whole thing, or one at a time. They give you the same asymptotic results. Okay, and I think yeah. So this is another general model which has been used actually recently. Again, you can see that it's a two-dimensional model. It has been used actually in the fingerprinting. Okay, so this is one of the nice model. Again, as I said, it's a huge implications what Professor Rao has shown the path. So these are the models which people can work on, and so it has been used for the fingerprinting one. So if we can develop a good estimation procedures, and it can be of enormous help for many purposes. Okay, I think with this, yeah, some of the references related to our work, which are the implications of this one. So these are some of the, yeah. So I think with this, I think I'll stop at that. Okay, thank you.